I would like to welcome you to the Dominique Cassini lecture of this year. And I'm particularly pleased to welcome Stamatios Krimigis, who is the medalist of this year, to give his lecture. Please, the floor is yours.
Thank you, Mr. President, and thank you all for coming at a time when you should be eating lunch. I appreciate the sacrifice, but that's what the schedule is like. So, I'm very grateful, needless to say, for this unique honor by the European Geophysical Union, and in particular that the fact that I also have an instrument on the Cassini spacecraft that is now orbiting Saturn makes it even more compelling in many ways and very appropriate. What I chose to talk about is the quest for discovery of planetary radiation belts. It's more of a historical talk, and it will start from Explorer 1 to Messenger. There is some early history in this that I was not exactly privy to, and I used as a source George Ludwig's book, which is called it was published by the EGU, Opening of Space Research, Dreams, Technology, and Scientific Discovery. And I actually knew George Ludwig personally quite well, and we talked about this before he left us a couple of years ago. And of course, I also had the privilege of being at the Applied Physics Laboratory all these years, where Van Allen had been before he went to Iowa to begin the effort that resulted in the Van Allen belts. So, just a basic principle of radiation belts. We have here is for those of you who are uninitiated, the fact that a charged particle is trapped in the Earth's magnetic field. It oscillates north to south, and it reflects at the strong magnetic field on either side. These are called the mirror points. The electrons also execute and the ions execute a motion around the Earth. The electrons drift east. You can think of it EE, east. The electron drift east. The ions drift west. And so that's really the basics of how you have a radiation belt. But it's interesting that, of course, nobody knew about this until the launch of Explorer 1, which was the first United States satellite to be launched in January of 1958. And the person who was the principal investigator and prepared the payload was James Van Allen, who eventually discovered the Van Allen belts. And he passed away in 2016. At that time, it was big news. He was on the cover of Time magazine, the most celebrated scientist, I would say, in the United States and the world. And what you see down here is the latest launch of the so-called Van Allen probes, the first spacecraft that actually honor Van Allen's discovery after so many years. And appropriately, they were built at the Applied Physics Laboratory where Van Allen had been, and we launched them on August 30 of 2012. You have already had a session here about the accomplishments of and the findings of the Van Allen probes, and it's just astounding that after so many years, nearly 55 years in the space era, the radiation belts closest to us and are still not that well known scientifically. So these are just some pictures of Van Allen. I'll spend a few minutes on that simply because he's I would say, the father of modern space science. A young man. Remember the Explorer 1 launch, and this is Pickering from the director of the Jet Propulsion Laboratory, Van Allen and Werner von Braun. This is at the Air and Space Museum. Van Allen in the later years, and then this last picture is on the 7th floor of the space building that was built by NASA at the University of Iowa after he had retired as department head. And this is an indication of his working space and a Frieden calculator for those of you who might remember such things in antiquity. And he was an exceptionally wonderful person. Just a little bit of his history. He worked as a fellow in the Department of Terrestrial Magnetism in Washington. And you remember many famous names: Scott Forbes, Harry Vestine, Chapman, and Bartels, famous geophysicists who had been there at one time or another. And then in 1940, the Department of Terrestrial Magnetism was asked to contribute their expertise to the war. And at that time, Johns Hopkins was asked and approved to establish the Applied Physics Laboratory for the purpose of advancing the work of the proximity fuse, and ML3 became its first director, and Van Allen on the staff. So Van Allen's job at the time was to develop a rugged, miniaturized vacuum tube that could withstand the 20,000 Gs and acceleration from a gunfire projectile. So you can imagine that you learn how to ruggedize electronics. And he became very good at that. Once the project was operational, he was commissioned a Navy lieutenant and was dispatched to the Pacific. Here's a picture of Van Allen in his uniform at the Applied Physics Laboratory, and this is the electronics at the time of the proximity fuse. So after the war, he established the High Altitude Research Group at the Applied Physics Laboratory because the US Army had brought over the remaining V2 rockets and invited the science community to actually, they said, we're going to fire these things. And if you all want to do some experiments, please feel free. And Van Allen, in that sense, was an opportunist for science. Whenever he saw an opportunity like that, he jumped right in and instrumented some of these. I'll show you a couple of pictures. At the same time, he began to lead the various panels of the United States government, and the last one being the Rocket and Satellite Research Panel in April of '57, which essentially was organizing the US effort in space before NASA was established in 1958. He left the Applied Physics Laboratory when he was asked to be the head of the Space Department, head of the Physics Department at the State University of Iowa in 1951, and he continued his research there, where they had many new and important findings. This is the High Altitude Research Group at APL with a V2 head in a payload section as they were putting things together. This is the first picture, actual photograph of the curvature of the Earth from a V2 rocket back in, I think, in 1946. This was the setup from the White Sands Proving Ground, which is a test site to this day. And then he went on to evolve a program of high-altitude research by combining a small sounding rocket with a balloon. And they called that Raccoon. Here, for example, you can see, I don't know if you can see, they let the balloon go, and under it was hanging a rocket. They were holding it until the balloon got high enough, and they let the rocket go. And typically, they were doing that from a Navy ship. This one happened to be in Antarctic in 1957. In fact, it was at the time when, after Sputnik was launched, Van Allen was on this ship, out of communication at the time. And there is a lot of history behind all of this. But what I want to point out is that there were good discoveries that came out of that. This, for example, is from one of those rocket flights, and it shows two sensors. One is a heavily shielded Geiger-Müller tube, and the other is one that was not very heavily shielded. It had a thin window. And as you can see, at some altitude, first of all, the altitude, by the way, is up here, and at about 70 kilometers, the soft radiation, the one that is not so shielded, takes off and reaches a maximum at the highest altitude of the rocket, and then repeats that. The shielded Geiger tube had this small increase and then down again. But what were they trying to do? They were trying to look at cosmic rays. And in the process, when they did all that, they found out that the relative intensity was a function of latitude. And lo and behold, guess what? You know, this maximum soft radiation was very close to the latitude of the aurora. And of course, we all know now why that was. Okay, let's get to the satellite era, however, and I wanted to show you this, this picture because it's very key to how the Earth's radiation belts were discovered. This is a digital tape recorder. Mind you, this is 1957-58, a digital tape recorder. It shouldn't be called a digital recorder, it goes on tape. But it was on the Explorer 3 spacecraft that was built at the University of Iowa. And you might say, well, what's the significance of that? You recall that the first satellite in space was Sputnik 1. It did not have any scientific instrumentation, so they couldn't possibly have looked at the radiation belt, found the radiation belts. But then they launched another one, Sputnik 2, I believe, was in November of '57. That particular spacecraft did have radiation detectors. However, the then Soviet Union did not want to allow any of the Western countries to track the satellite and decode any of the data, so they only relied on ground stations in the Soviet Union, and it so happened that the spacecraft was at its lowest altitude and didn't see much of anything. So that's how Vernov missed having found the Vernov belts. So, Explorer 1. Here comes Explorer 1, well instrumented for that kind of thing. However, it also suffered from a very peculiar phenomenon. There were various stations around the world that could get the data down. And what they observed is that the counting rate of the detectors would start climbing, and then it would go to 0. And they scratched their heads because what they were trying to do is look at cosmic rays. Why would they go to 0? And so then they started trying to get global coverage by doing this tape recorder, which flew on Explorer 3. And this is Van Allen's plot in a hotel room of data from a chart recorder. And it shows the count rate, and then it starts increasing. And it gets to 128 counts per second, and then it stops increasing. And then, and of course, there is altitude here. This is time, but it's altitude. And on the other side, it comes down from 128 counts per second, because that was the counter that they had that could record the radiation. And it flattens out. There's a fascinating story about that in George Radwick's book. And they decided to, at the suggestion of Carl McLuhan, to put one of these Geiger tubes in an X-ray beam, which they had borrowed from the university hospital, and they were using. And when they did, and they increased the beam intensity, what happened is they counted more and more X-rays, and then the rate went to 0. As the intensity of the X-rays went up, as the counting rate of the detector kept increasing, then it dies. And once they realized that, this is a note from Ernie Ray, one of Van Allen's collaborators. They realized that there are huge amounts of radiation up here, and that's why the detector was flattening out and then dropping to 0. And there's a note 4558, 1958 gamma, that was Explorer 3, data. Space is radioactive. And he drew this particular donut in a note to Van Allen. These are the protagonists, McLuhan, Van Allen, George Radwick, and Ernie Ray. These three are gone. Carl McLuhan is the only one who is surviving. But, and by the way, you recall that the data, especially for the youngsters in the audience, it was a stripped Charles recorder. You got to put your ruler and count the space between pulses so you can deduce a counting rate. And the first initial sketch of the Van Allen belts, the inner zone, the outer zone, this was, and that's where the publicity came from. And the name Van Allen belts, by the way, was coined by the media. It was not, Van Allen never called them that, but it got stuck, so to speak. Now, these days we're all very proud of spacecraft that can be built at the universities. This is a stack of 3 spacecraft that were launched in 1961, you know, 2-3 years after the first American satellite, 4 years after Sputnik. At the Applied Physics Laboratory, Van Allen's old laboratory, and mine, of course, for many years, they had discovered how to do Doppler navigation, and they built a transit satellite system, which then could, using Doppler, localize a ship or a person on the surface of the Earth. This was the precursor of GPS that we are used today. And they asked Van Allen, say, you know, we're very busy and we want to measure the environment. Why don't you build a small satellite at Iowa and we'll stick it on a stack? This was, by the way, a Navy satellite, which at that time was an signals intelligence satellite. I think it's now unclassified, so I can talk about that. And they launched this stack. So this was the first university-built satellite, for those of you who are interested in that kind of history. This is Dan Garnett, many of you know, with Engine 3, and it's the first VLF, very low frequency receiver, that was ever flown in space. And we could actually hear the waves, and Paul Kellogg knows these well, from space. Don was, at the time in '62, a junior in college. He was also the system engineer for this spacecraft. And this was sort of my third instrument after the Mariners. We launched that on Explorer 33 in 1965 with Van Allen. This is Tom Armstrong, one of my colleagues and fellow graduate students. Now, fast forward to today. Here we are with a relativistic electron storage ring embedded in the Earth's outer Van Allen belts from the Van Allen probes, Baker et al. Science 2013, last year, the typical belt structure, and the third radiation belt that was a transient one, but it was discovered just last year. So we're learning things. But go on with the story. When I arrived in Iowa City as Van Allen's graduate student in '61, at the end of '61, the theories of the day were, now all planets have radiation belts, and where do we go first? Where do we go to Mars? And as soon as I finished my master's thesis, Van Allen calls me in and says, how about building a solid-state detector to send to Mars? And I said, well, I don't know how to do that. And he said, don't worry, you'll learn. And that was his teaching method, throw you overboard and see if you could swim. I had to swim very hard. The outcome was this device called Trap Radiation Detector, TRD. This was the spacecraft built by JPL, needless to say. There are two spacecraft, Mariner 3 and Mariner 4. Mariner 3 never made it very far because the heat shield melted over the payload. Mariner 4 was successful, and we got to Mars. And on July 15, we were watching the data come in. Again, you might wonder, what are we watching? Well, we're watching a strip chart recorder and seeing whether there are any pulses coming in and how fast they were coming in. And this was our instrument engineer and Bob Lockhart and several other people. Well, here's the data. And it was, what a disappointment, We went by Mars, and this is the count rate of electrons that we expected, that we were counting. And at the point of closest approach, there was nothing there, except there was some activity in protons on a solid-state detector that I had built, but this didn't seem to be associated with Mars. There seemed to be some increase that had to do with some solar protons that were emitted by the sun. But what we did is to do a scaling argument. I don't know, I'm not watching the time very much here. 20 minutes. Okay, so if we simply equated the solar wind pressure with the standoff distance, which is proportional to the square root of the magnetic moment over the distance to the 6th power, and we use the scaling relationship to draw the putative magnetopause based on a scaling from Earth. And when you do that, you find out that the absence of any electrons meant that we went outside the magnetopause and at the closest approach. And the scaling was that the magnetic field, the magnetic moment of Mars divided that by the Earth was about 1/1000th, or as an upper limit. So you might say, what did you learn from that? At that time, what was popular was Brackett's law, which stated that the angular momentum of the planet was proportional to, or the magnetic moment was proportional to the angular momentum. And so if you actually took that seriously, that was the only guidance, by the way, about how you do magnetic field scaling among planets. If you took that seriously, then the magnetic moment of Mars will be 0.03 or so that of Earth. So this was a very useful upper limit. It wasn't that at all. And that was the first involvement that I had in knocking down models. But here's the things that we said at the time, Van Allen being the leader, of course. What do they mean? It means that the equatorial surface magnetic field of Mars is less than 200 gamma, and perhaps less than 100, and hence suggests that the solar wind will, on occasion, and perhaps usually, have a direct interaction with the Martian atmosphere. Does that sound familiar? This interaction may be of essential importance in determining the physical state of the atmosphere. It is also evident that the atmosphere and surface are exposed to the full effects of solar and galactic cosmic radiation irrespective of altitude. Well, as we all know, these are two statements today. The current view, one of the current views of the interaction of the magnetosphere of Mars with the solar wind is given by this. I found this in the last website. And there is a magnetic pileup boundary, but there is no question that the solar wind impinges. We have crustal magnetic fields, but no core magnetic field at Mars. And if you take this at face value, the magnetic field of Mars on a global scale is 800 times smaller than that of Earth, namely 0.001, which is what we had inferred at the time. Now, the next, we rebuilt the spare instrument and flew it on Mariner 5 to Venus. We did essentially the same thing, we did the same thing, the same kind of scaling, and we ended up with an upper limit there for the magnetic field of Venus. We all know that now the interaction is mostly ionopause and flux ropes, and there is a bow shock of sorts, but in fact there is no intrinsic magnetic field at Venus. Mercury. That was a puzzle because a few years later, in 1975, Mariner 10 flew by and turned out that Mercury did have a magnetic field, and one of the detectors decided that there was huge fluxes of electrons and protons and so on. Some of us disputed that at the time. This is kind of today's version from the Messenger mission, which is now in orbit. And it is a complex environment. There's space weathering. There is indeed a magnetosphere. There is a sodium trail to this. But I did want to show you, when you look for radiation belts, this is the kind of stuff that we found. These are months worth of data, and it has been repeated ever since. There are all these spikes of electrons every time you go by the planet, close in. But they are up and down all the time. And of course, the modeling that has been done all these years is we take the Earth and then we make something like that for any other planet. And this is one of the models from Slavin et al. And the big thing, as you can see, is that Mercury occupies a very large volume within the magnetosphere. And that changes fundamentally the way the particles do behave. One of the big findings by Messenger was that actually the magnetic equator is not at the center. It is offset by about 4,000 kilometers, almost exactly. And therefore, you have a lot of activity on the northern hemisphere and northern auroral zone, if you like, of that planet. So the plasma hits the southern hemisphere and sort of gets stuck up here and reflects. And if you look at the distribution, we see all these events at different locations. This is This is solar direction, north direction, and they're distributed like this, and they depend on energy. But the most important thing is that they're really transient events. They go up and down, and the best measurements that we have so far are a few milliseconds. And at a few millisecond time scale, you see these things going up and down, up and down. So the safe conclusion is that there are no durable radiation belts at Mercury, in spite of the fact that that planet has a magnetic field. Voyager, of course, completed the exploration of the outer planets. I'll just go through here quickly. Jupiter's magnetic field, 10 times bigger than Earth's, and the role of the field-aligned currents from the moons to the aurora. This is an image that we took as we went by with Cassini, by Jupiter, flying by Jupiter to get to Saturn. And this is a schematic of what actually happens there, which, of course, was delineated in great detail eventually by Galileo. But you have cold plasma that is coming from the volcanoes of Io, and you also have a lot of pickup ions and a hot neutral wind, and lots of sodium out here. In fact, when you look at the composition, you see that you have oxygens and sulfurs and SO2 and so on. In a very nice piece of analysis by Barry Mock and his colleagues, it was possible to look at the images and decide that there is a torus around Europa. And now, of course, this year we found out that there's actually activity in the south pole of Europa. So who knows exactly how this is happening and in what way. Then the big surprise, Ganymede has its own magnetic field. We were able to measure the angular distribution of the electrons, the pancakes, these butterflies, and so on, all classic signatures of a trapped radiation belt, if you like, right within the magnetosphere of Jupiter. This is the idea that what we drew up before we got to Saturn with Cassini. And of course, again, you can see the similarities with Earth. And one of the things that we have emphasized is the fact that because there is so much dust and gas in the magnetosphere of Saturn that was well known, you have a lot of interactions between the energetic particles and the neutrals, and the energetic particles escape as neutrals. We call them ENAs, energetic neutral atoms. But to the basic thing, Saturn radiation belts, yes, of course. There are Van Allen belts at Saturn. They are sculpted by the moons, the inner moons. And we understand very well how these come about, because cosmic rays hit the upper atmosphere of Saturn. They generate a lot of byproducts, including neutrons, which decay, and they become protons and electrons, and they get trapped in the magnetic field, and the protons are absorbed, the electrons are not. So that's how we end up with radiation belts, and we understand them well. Now, one of the things that I wanted to show you, nothing new under the sun, this is from a paper by Roussos et al. And back in 2005, in addition to the normal radiation belts that we had seen, again, with the moons embedded, we also saw this new radiation belt that showed up, stayed around for a few weeks, and then it went away. And guess what? What did I show you about the Van Allen probes earlier? It's almost the exact analog of what's happening at Earth, and it's there at Saturn. Okay, now I could if we can get out of the PowerPoint and play that movie. I was not, it works? No, it doesn't. Well, let me say what I'm trying to show you. What you will see here, this is looking down on Saturn, and this is the aurora as measured by, the UV aurora as measured by Cassini. And this is a cloud of neutral atoms that are emitted. And out here is the spectrum of radio waves at Saturn that you can actually hear if we're successful. Okay. I had it open a minute ago. I don't know if the sound is going to play. What you see here is that there is an explosion from the magnetotail that increases. You see the increase in aurora emissions, and you see the increase in the big burst of sound. I don't know that I can make that. I'll just play this once more and see if I can also start the sound, but it may not be possible. That's the sound went away. If we click on this, it might be possible to play it again. Oh, strange things happen. Anyway, we're going to run out of time. So what I attempted to show you is that we now have the capability of actually taking an image of the magnetosphere. This is an example of that. We can see when things happen, where they happen, how long they last, and how they move. And this has been, are we back in the PowerPoint? Next slide. If we can hit the next slide. Okay. So this is our present-day image of the magnetosphere of Saturn. It has huge dimensions. This is like 12 million kilometers from the solar wind all the way to the tail. There is rotating plasma that we have documented with various movies. There is a plasma sheet that curves upwards on the night side, and there is plasma that jumps out into the heliosheath, into the magnetosheath, and upstream as it moves around. One of the things that I didn't talk much about has to do with how we identify what kind of plasma we have. And this was with the instrument on Cassini, where you can see that as we went by Earth, we have a lot of nitrogen and oxygen. We touched a part of Jupiter's magnetosphere, but not very close in. We have all kinds of ions of oxygen, various charge states, and sulfur. And then at Saturn, we have lots of water, as we expected. And it shows you how this technique of looking at the charge state and the identification of the ions is powerful in deciding where the plasma is coming from and how it's accelerated. This is the radiation belts of Uranus. As you know, Uranus's spin axes are in the ecliptic plane, unlike any of the other planets. It does have radiation belts. They also do carve out corridors in the radiation belts by the moons of Uranus. And then finally, Neptune. This is kind of an example of what we observed as we went by in 4 days through the Neptune magnetosphere with Voyager. And you can see the increase in intensity of both the protons and the electrons here. This is the color bar. And you also see that this here is Triton, and it's the orbit of Triton. And as you can see, it essentially limits the extent of the magnetosphere and the radiation belts by its orbit. We have drawn a schematic of this magnetosphere. It so happened that the magnetic moment, the magnetic axis of Saturn is very much offset. And at the time we went by, it was pointing pretty much in the direction of the ecliptic plane. And again, here's the orbit of Triton that delimits the Van Allen belts at Neptune. This is just a synoptic view of planetary magnetic fields, and I didn't have time to put in their messenger now. But you can see down here the tilts. Saturn's Jupiter's is only about 11 degrees. Saturn's is pretty much aligned with the actual spin axis. Uranus, on the other hand, is way offset from the center, and Neptune is almost in the South Pole in terms of where it's at, 55% of the magnetic axis. And its magnetosphere, I will not bother you with all of this. The point here is that most magnetic field models were thought to be understood in terms of the spinning and dynamo and so on. And it turned out that they simply do not work. The dynamo theory simply does not work and could not predict any of these findings from Voyager for these planets. And dynamo theory is in a sorry state even today. Comparative magnetospheres, what is shown here is the magnetosphere of Earth. But if we put the magnetosphere of Mercury on the same scale, it looks pretty small. On the other hand, if you put the Earth's magnetosphere, say, in the same scale as Neptune's, Earth's is pretty small. If you put Uranus and Neptune in the same scale as Jupiter and Saturn, they look very small. And this is the dimensions of the Sun compared to the magnetosphere of Jupiter. So the magnetosphere of Jupiter is the largest object in the sky. If we could actually view it, it would look like a full moon if we could actually have a visual impression of it. So the solar system magnetospheres, and I borrowed this slide from Michel Blanc, who I believe gave this lecture in 2004. We have the heliosphere. Now we have intrinsic magnetospheres. All the giant planets have it. So does Ganymede within an intrinsic magnetosphere. And then there are some induced, like Europa's, for example, if you want to call it that. Of course, Earth's and Mercury's. Mars, at the time, it was still a question mark. I want to say a few words and close with the heliosphere, because it's a remarkable story and it has to do with the Voyager mission. What you see here is a plot of ion intensity from 1977, when Voyager was launched, to the present time. This is a logarithmic scale, and you see that at the orbit of Earth we have these kind of intensities, 10 to the 6 or a few times 10 to the 6. Obviously, the Sun is the source, and then it kept decreasing, and back in 2000, 2001, we began to see increases, and then eventually we crossed what was called the termination shock by Voyager, and there was a big increase, and the levels were almost the same as at 1 astronomical unit. And and these, by the way, are the cosmic rays, and they kept on increasing as well in the solar cycle. Now, this pink line is Voyager 2 on the same channel, and it works very well in terms of intensities. Voyager 2 crossed after Voyager 1, because Voyager 1 is faster. On August 25 of 2012, the intensity dropped like a rock. We couldn't see anything anymore. And then Voyager 2 kept on going, because it's in a different part of the heliosphere. And I just want to show you this particular diagram, which plots the cosmic rays outside the termination shock. Here's, pardon me, the heliopause. When we got out of the into the galactic space, some directions, namely along the magnetic field in the galaxy, were flat, as you would expect cosmic rays to be. However, the direction perpendicular to the magnetic field were substantially less. And those of you who know about Fermi acceleration of cosmic rays, they're supposed to be totally isotropic in random magnetic fields. And here we have a case which in many ways reminds us of a kind of a closed magnetic field system where the cosmic rays listen and obey the direction of the magnetic field and they are not isotropic. This remains a big issue to the present time, and the anisotropy is pretty substantial. Nobody understands that. This is a schematic that shows that now that we're out, that there is this big belt of particles around the heliosphere. So one could say that there's another belt beyond the magnetospheres. And if we summarize the findings, this is from an old paper, but it's still current in many ways, and it shows how the dimensions of the magnetospheres and the satellites that are embedded in its magnetosphere. So I'm mindful of the fact that we finishing up. But under radiation belts in the solar system, what do we have? 5 planets with intrinsic magnetic fields have belts. They have belts. It's quite clear. Earth, Jupiter, Saturn, Uranus, and Neptune. 1 planet with intrinsic magnetic field has transient electron bursts, but no durable belts. Also, Ganymede has intrinsic magnetic field. No belts in the sense that they're not really distinguishable as associated with Ganymede. Venus and Mars do not have radiation belts. Pluto is unlikely to have belts, and we must wait for the New Horizons encounter in a little over a year to find out for sure. But I believe that's probably the case, that it is unlikely to have belts. And the Voyagers have found a belt surrounding the heliosphere that extends from about 90 astronomical units to 122 astronomical units, which is really a remarkable set of findings in the heliosphere. Now, the magnetospheres are accessible laboratories for astrophysical processes, and we use all that we learn that is available to us in situ to do astrophysics. And I list here some of the processes that we study, and all of you study and write many, many papers about, and I didn't talk about any of that. But the fact of the matter is that that informs what we can and cannot do in astrophysics. So, to conclude, this was a picture from Van Allen Day in Iowa City on the occasion of his 90th birthday on October 9, and it was outside Van Allen Hall at the University of Iowa. This is Carl McLuhan, George Ludwig, who passed away, Frank McDonald, who passed away. There are a few of us that are surviving here. You can see a lot of the sort of luminaries of the magnetospheric business, known as Lou Lanzarote, Jim Parker, Sue Nakasofu, and so on. There is a new generation of people that are coming on to carry on this kind of work. But we have to remember that it is this man's ingenuity and inspiration and hard work that made it all possible for us. Thank you, and I thank you, the EGU, for this unique honor.